morning, students. I'm Chaitanya, Assistant Professor in Mathematics in Institute of Aeronautical Engineering located at Dundigal, Hyderabad. As a part of our course curriculum, the probabilistic modeling and reasoning, today we are going to discuss the concept of singular value decomposition and its application in machine learning and image processing. So, let us look into the concept in detail. So, before learning what is singular value decomposition of a given matrix, we must have a fundamental knowledge of eigenvalues and eigenvectors. So, I'd like to start with the concept of eigenvalues and eigenvectors and its fundamentals. Then I'll proceed to the singular value decomposition. Now, here I'm considering a matrix 5, 4, 1, 2. It's a 2 by 2 matrix. And I'm considering two column vectors, 2, minus 1, and another vector I'm considering is 4, 1. So I have a matrix which is a 2 by 2 matrix, and I have two column matrices which I call as column vectors, the vector x and the vector y. Both are of size 2 by 1. Now, first I'd like to project them on an xy plane. That means I'm going to plot the vector x on xy plane. If you project the vector 2, minus 1, here you'll see 1, 2 and minus 1. The vector will be here, and hence you can locate the vector as this column vector. This is 2, minus 1. Now let us multiply the vector x with the given matrix A. What happens if you multiply the given vector 2 minus 1 with the given matrix A? The product will be 5 into 2 plus 4 into 1, 4 into minus 1. That is 6. 1 times 2 and 2 times minus 1. That is 0. So after multiplication with the matrix A, the vector x has been changed to 6, 0. If you locate the number 6 on x-axis, then the new vector is 6, 0 is like this. So when we have projected the vector x and its resultant vector ax on xy plane, the original vector x is from origin, it is going in this direction with size ox, and the resultant vector ax is going along with x-axis like this, along with x-axis, okay, which is 6, 0. This is 2, minus 1, this is 6, 0. Okay. That means here we are observing that the vector has changed its direction. Initially it is going in this direction. But after multiplication with A, it has changed its direction. Initially it is going in this direction, but once you multiply with A, it has changed its direction to x-axis. So it has changed its direction. Now let us take the case of y and let us look what happens in the case of y. So first, I'd like to project the vector y on xy plane. The vector y is 1, 2, 3, 4. Say this is 4 and this is 1. So the vector 4, 1, that is y. This is our vector 4, 1. Okay. So this is our vector 4, 1. Okay. This is y. Now let us multiply y with A. Then we'll get 5, 4, 1, 2 into 4, 1. When we multiply these two matrices, this results into 5 into 4 plus 4 into 1, that is 24, and 1 into 4 plus 2 into 1, that is 6. That means it is nothing but 6 times of 4, 1. That means If you project this, something here you can find 24. Sorry, here you can find 24, and here you will find 6, and hence the vector will be, the resultant vector will be, this is 24, 6. Here what do you observe? Here the original vector is 4, 1, and the resultant vector is 24, 6. Both are in same direction. That means the vector doesn't change its direction when multiplied with A. Y doesn't change its direction. It is continue. Initially it is 4, 1. After multiplying it with A, it is continuing in the same direction, 24, 6. That is, the vector doesn't change its direction, which is showing a good behavior, which is called eigenvector. Eigenvector. So here we have seen that the vector x has changed its direction. Initially it is going in this direction. Later, after multiplication with it is changed its direction. But the vector y, initially it is going in this direction. After multiplication with y, it is continuing in the same direction. This kind of vectors are called eigenvectors. So eigenvector of a matrix A is nothing but a vector which doesn't change its direction even after multiplied with A. Even after multiplication with A, it doesn't change its direction. That kind of vectors are called eigenvectors. And now, what is eigenvalue? If you see, so we have observed that the vector 4, 1 before the multiplication with A, 4, 1, and after multiplication it is like this. This is our 24, 6. Okay. So if you take 6 table common, 24 and 6. What is the table common? 6 table. Then it is 6 into 4 common. That is 6 into y. That means the vector is continuing in the same direction and its magnitude has been raised to 6 times. That means 1, 2, 3, 4, 5, 6. The magnitude is extended to 6 times. That means ay is equal to 6y. After multiplication, the vector is in the same direction, but its size has been extended to 6 times. Y is extended to 6y. So, how many times it is extended? That is called eigenvalue. 6y. Okay. So, that is called eigenvalue. So, eigenvalue denotes the length of the vector, whether it is extended or contracted. Sometimes it may be continued in the same direction, but sometimes it may extend or sometimes it may contract. Same direction, but it may extend or it may contract. So, the lambda value denotes the size, how many times it is being extended or how many times it is being reduced. If lambda is less than 1, then we say that the vector has been reduced. Okay, and if lambda is greater than 1, we say that the vector has been extended. Okay, in this way we can understand geometrical interpretation of eigenvalue and eigenvector. Now, let us summarize these things into mathematical definitions. So, whenever we have a matrix of size n by n, which is a square matrix and non-zero matrix, then a non-zero vector x is said to be an eigenvector of A, if there exists a non-zero real lambda such that Ax is equal to lambda x. Simple, what we have discussed now. We discussed that eigenvector which doesn't change its direction. It continues in the same direction even after multiplying. Okay, so that is what we have represented in this equation. Ax is equal to lambda x. That means before multiplication the vector x, and after multiplication it is lambda x. That means it doesn't change its direction. Okay, and the number which is represented by lambda is called eigenvalue. So lambda is called eigenvalue of x of A with respect to the vector x. That means number of times the size has been increased or size has been reduced. This is what we express the mathematically the definition of eigenvalues and eigenvectors. Okay, and we have a procedure to find eigenvalues and eigenvectors. I'll just mention the procedure, then we'll go to our concept singular value decomposition of a matrix. Uh, when we have a square matrix, we must note a point that eigenvalues and eigenvectors exist for only square matrices. Okay, not for rectangular matrices. When we have a square matrix of size n by n, and then automatically we can construct a matrix A minus lambda I. Okay, by subtracting lambda times the identity matrix. Okay, then we get a new matrix which is called the characteristic matrix of A. Characteristic matrix of A. And if we calculate the det of this new matrix, that is the characteristic matrix, we will get a polynomial in lambda of degree n, which is called characteristic polynomial, Okay, and when we equate this polynomial to 0, we get an equation. Automatically, when we expand the det of A minus lambda I, it becomes a polynomial in lambda of degree n. Because the matrix order is n by n, automatically we get a polynomial of degree n. And if we equate it to 0, it becomes an equation that is called characteristic equation. And once we get this characteristic equation, we can solve that equation. Once we get this equation, we can solve it. And we can find roots. And the roots are called eigenvalues. Denoted by lambda 1, comma lambda 2, so on lambda. Because it's nth degree polynomial, it will have definitely n roots. Those roots are represented by lambda 1, lambda 2, so on lambda. These are called eigenvalues. So this is the way how we'll try to calculate the eigenvalues. Once we get these eigenvalues, we will solve this homogeneous system. That is Ax is equal to lambda x. That is A minus lambda I into x is equal to this. We solve this homogeneous system and we'll get answers which are called eigenvectors. Because this is homogeneous system, and we can solve this by using rank methods or row operations or Gauss Jordan, and we can find the solutions which are called eigenvectors. So this is the mathematical orientation about eigenvalues and eigenvectors. Now, see, if you see here, you can check there are so many colors of vectors which are originally which are like in some direction and in some size, but after multiplication they are expanding. Okay, in this diagram you can easily observe, but you can observe that these blue vectors are not changing their direction, they are continuing in the same direction. Okay, whether the plane is expanded or whether the plane is original in the original shape, whether it is expanded, the direction of blue vectors are not changed. Okay, but the red vectors, if you keenly observe, before expansion it is going in some direction, and after expansion it is going. Before expansion the vector is like this, but after expansion the vector is like this, red vector. But blue color vectors are not at all changing their directions, they are continuing the same direction before in the original plane as well as in the expanded plane. The expanded plane represents the multiplication with A, and the original plane represents without multiplying A. Okay, so these blue vectors which are not changing their directions even after multiplied by A, that means even the plane has been expanded, those vectors are called eigenvectors. So this is how we can see the eigenvectors. And okay, and So the multiplication of a matrix, now we are going to the details one by one, and which leads to strong foundation for singular value decomposition. The multiplication of a matrix and a vector produces another vector, which is defined as transformation. When we multiply two matrices, say matrix A, matrix X, then automatically it results into another vector, okay, say X dash, which is called a transformation. So this A transforms X into X dash. That is what he's saying. The matrix A is transforming X into X dash. Okay, and however, there exist some vectors for some given matrix such that their direction doesn't change. So what do you say? Ax is equal to lambda x. That means x is not changing its direction. X is continuing in its original direction even after multiplied by a. Even after multiplied with the transformation a, it is not changing its direction. Such kind of vectors are called eigenvalues, and this lambda is called eigenvalue. So this x is called eigenvector, which doesn't change its direction, and the number associated with x is called eigenvalue. Okay, so that is about GIF, means the diagram which I have shown you like this. Here you are observing that the blue vectors are not changing their directions, even the plane has been extended with the help of a, and originally the plane is like this, and when it is expanded the plane is becoming like this, like rhombus. Originally it is like square, and when it is expanding it is becoming like rhombus, that means multiplied by a. But the blue vectors are continuing in the same direction, whereas the other color vectors are changing their directions. Okay, that is what difference between eigenvectors and non-eigenvectors. Okay, now what is a singular value decomposition? How it is important in machine learning and artificial intelligence? Okay, um, see, first let us look into the definition of a singular value decomposition of a matrix. Every matrix, whether it is a square or a rectangular, every matrix can be decomposed into product of two matrices, which are like matrix U into matrix D into matrix V transpose. That means every matrix, whether it is square or rectangular, any matrix can be decomposed into product of three matrices, namely U, D, V transpose, where U is an orthonormal matrix and V is also an orthonormal matrix formed by eigenvectors, and this is also formed by eigenvectors of some matrix. We will come to know the details. And D is a diagonal matrix. D is a diagonal matrix. So we are decomposing A into product of three matrices, where the first matrix U is an orthonormal, and D is diagonal, and V is also orthonormal, and its transpose V transpose. So this kind of decomposition is called singular value decomposition. Why it is named singular value decomposition? Because see, the middle matrix is a diagonal matrix. Here, the entries of these diagonals, that means the entries of the diagonal matrix D, see, the entries of the diagonal matrix D, okay, the D will be like this, right? If it is 3 by 3. These entries are called singular values. These entries are called singular values, and hence the decomposition is called singular value decomposition. So the name comes after these diagonal matrix entries, and which are called singular values, and hence the decomposition is called singular value decomposition. Okay, and here we have to note that the diagonal entries, that means these entries are always positive reals. They cannot be negative, they cannot be zeros. We'll see how it happens, everything. Okay. Now, what are the uses of SVD? What are the applications of SVD? SVD is useful in many tasks, in many applications. The precise and very much concerned application to our subject is the data matrix A is close to a matrix of low rank, and it is useful to find a low rank matrix which is good approximation to the data. That means simply dimensionality reduction. Yes, we are mostly concerned with mathematics which help us to reduce the dimensions, and so that we can save our storage space and time. That is what we are more concerned with machine learning algorithms. So here, by using SVD, we can uh, reduce a big size of matrix, data matrix, into reasonably small size of matrix by using SVD. By using singular value decomposition, when we have a huge big data matrix, we can reduce it to a smaller data matrix without loss of much valuable information. The essence will be preserved same, but the dimensions will be reduced. Initially, it may be m by n, later it may be reduced to r by n. So it will be compressed, but the data will be preserved. That is the beauty of dimension reduction, and in that SVD plays a vital role. That is why we are going to learn this. Okay, and here you can see a diagrammatic explanation of singular value decomposition. When we have a data matrix of size m rows and n columns, see here we have m rows and n columns for data matrix A. The data means it may include hashtags, word occurrence, there may be words, hashtags, all these combinations will be there. Now, here uh, we here in the data matrix we are considering words as rows. The rows are represented by words and columns are represented with hashtags. This is the construction of this diagram. This diagram is like rows represents the words and the columns represent hashtags. Then we are decomposing this matrix into product of three matrices, which is first matrix is represented by pink color, where the original matrix is blue color, and the middle matrix is of white mixed with the dark blue, and the right side matrix is a red color matrix. Okay, now here we are dividing it into three matrices, where the pink color matrices is embedding of hashtags by the words they co-occur. That means the embedding the hashtags by the words they co-occur with, and the right side matrix is embedding the words by the hashtags they quotes. Okay, so this precisely concentrates on the hashtags. Okay, and this right side matrix precisely concentrates on the words. Okay, and the middle matrix is called singular matrix because it's a diagonal matrix. Only diagonal elements will be non-zero. Okay, and these non-zero values are called singular values, and these singular values will decide whether we have to decompose it further or we have to stay itself in the same stage. Okay, this is about a small diagrammatic explanation about singular value decomposition. Now, let us see the features of singular value, handy mathematical technique that has application to many problems. Singular value decomposition not only concerned to machine learning, it has so many applications in mathematics. It will be used in medical image processing. It will be used in historical image processing, and it has applications in solving least square equations, some linear equations. So many applications practically. But it is handy mathematical technique. It can be easily programmable because matrices, we are using simply matrices. We have to know matrix multiplication, matrix transpose. So we can easily program and we can easily handle the computations with the help of a computer by programming this SVD. Okay, and given any m by n matrix A, the algorithm to find matrix U, V, W, C, which I have told you, okay, A is equal to U, W, V transpose. Okay, U is orthonormal, V is orthonormal, and W is a diagonal matrix, which I discussed with you. Okay, so this is how we can see that A is equal to U orthonormal. But I'll explain what is orthonormal. I'll just recap because we have discussed in the last class what is orthonormality of vectors, what is the orthonormal, what is the meaning of orthonormal matrix. I'll just recap it once. And this is a diagonal matrix with the diagonal limits W1, W2, so on, Wn. And this is again, V is also an orthonormal matrix. We're taking the transpose. Now let us just discuss what is orthonormal matrix. See, suppose I'm having U, which is of three. You can say that which is which is of a 3 by 3 matrix of columns Q1, Q2, okay, Q1, Q2, Q3. Let us assume, let us see that these columns are behaving in this way. Q1 dot Q2, dot product of two vectors. If we have Q1 as A1, B1, C1, Q2 as A2, B2, C2, okay, and Q3 as A3, B3, C3. Orthogonality means the dot product is 0. That means Q1 dot Q2 is 0 and Q2 dot Q3 is 0 and Q1 dot Q3 is 0. So orthonormality means the combination of two things, orthogonality and normality. First we are saying orthogonality. When do you say U is orthogonal matrix? If the dot product of every pair of columns, that is Q1 dot Q2 is 0, Q2 dot Q1 is 0, Q3 dot Q1 is 0. Can we have such kind of matrices? Let us see an example. Yeah, I'm going to take this matrix 1 0 0, which is well known to us, 0 1 0 0 0. If you take these two matrices, if you make dot product between the vectors 1 0 0 and 0 1 0, what is the dot product? First into first, A1 A2 plus B1 B2 plus C1 C2. That means 0 plus 0 plus 0. The answer is 0. That means these two columns are orthogonal. In the same way, we can verify that the dot product of these two is 0 and the dot product of these two columns 0, and hence this entire product, the identity matrix, is always orthogonal because every pair of columns is orthogonal. Dot product is 0. Okay, so we have an orthogonal matrix like this. Now, suppose we have a vector 1 2 3. Then what is the norm of this vector? Norm of x is denoted by norm x, nothing but root of 1 square plus 2 square plus 3 square. That is root 13. So when we divide every element of this vector by root 13, okay, then we'll get a new matrix, new vector. Say I am dividing every element of x with the norm 1 by root 13, 2 by root 13, 3 by root 13. This is called normal vector, normalized vector. So x is a vector where x bar is a normalized vector because we are dividing every entry of x with its norm. Norm is root of a square plus b square plus c square. So now when do you say a matrix U as an orthonormal matrix? When do you say a matrix U as an orthonormal matrix? Is if we have Q1, Q2, Q3, 3 columns, and first condition, the dot product should be 0, that is orthogonality. Q1 dot Q2 is 0, Q2 dot Q3 is 0, Q3 dot Q1 is 0. That is orthogonality. Every pair is orthogonal. Okay, and second condition, norm Q1 is 1, norm Q2 is 1, and norm Q3 is 1. If the matrix U satisfies these two conditions, that is orthogonality and unit normality, okay, then that matrix is called orthonormal matrix. Okay, so in our orthonormal matrix, so in our singular value decomposition, we'll decompose the given matrix A into product of 3 matrices U, D, V transpose, where U is orthonormal, V is orthonormal. Okay, and we are taking the transpose of this orthonormal, and D is a diagonal matrix. That is what we have represented here. Okay, now the WIs are called, here we can see these W1, W2, Wn, the diagonal elements of the diagonal matrix. These are called singular values, and hence it is called singular value decomposition. Okay, and generally here he is proposing an important property of these singular values. When we have a matrix M by N and we have decomposed it into U, D, V transpose, that is singular value decomposition, and here D, in this D will have some singular values like this, w1, so on, wn. Among these n values, only r values, that means among w1, w2, w3, so on, wn, only up to r will be non-zeros. Remaining will be 0. That means rank of A, if rank of A is r, so only r, first r values will be non-zero and remaining will be zeros. Need not be first r, but r singular values will be non-zero and remaining singular values will be 0. So it is decided by rank A. Out of n singular values, r values will be non-zero and remaining will be 0, where r is the rank of A. Okay, and now SVD and principal component analysis. We have discussed principal component analysis. That means when we calculate when we have a numerical data matrix, we can calculate variances and covariances. In the first video, I have discussed how to calculate a covariance matrix. And principal component analysis means for that covariance matrix, suppose this is a covariance matrix, we have covariance matrix, say A of order m by n, or say it is a square matrix m by n. Then we can find eigenvalues and eigenvectors, right? So it will have n eigenvalues, lambda 1, lambda 2, so on, lambda n. Among these eigenvalues, one will be the largest absolute. That means if you take modulus for each eigenvalue, one of these will be the largest one, say lambda 3. The corresponding eigenvector, say x3, gives us the principal direction, which is represented by this red line. So when we have a covariance matrix for the given data matrix, we can calculate covariance matrix, which we discussed in the first video. And for the covariance matrix, we can calculate eigenvalues and eigenvectors. And the largest absolute eigenvalue gives us the eigenvector, which is called principal eigenvector. And the direction represented by that vector, here this red line, is called the first principal component vector. And if you take the perpendicular vector, which is represented with this blue line, which is this blue vector, that is called second principal component. So first principal component is the vector with highest magnitude among all eigenvalues. Okay, the eigenvector corresponding to the highest absolute value eigenvalue, and its perpendicular eigenvector is represented by blue line. These two are called principal components. Okay, and these principal components tells us in which directions we have to process the data. Okay, that is why this is called principal component analysis. Now here you can see the red points shows you the principal axis direction, that is the highest eigenvalue, the biggest eigenvalue, and its corresponding eigenvector direction. Okay, and you can see a perpendicular line which shows the second principal component direction. Okay, and remaining points will be gathered around these two directions, and these two directions will cover most of the points in the data. Okay, they will show what is the amount of variation in the sparse data matrix. Okay, so this is what we discuss now, the singular value decomposition, UVD, and here we are going to see what happens in singular value decomposition, how we reduce the dimensions, how it is used in the dimensionality reduction. That is what we are going to see. How we are going to apply SVD in dimensionality reduction. With the help of small example, I'll explain. See, here we are considering a matrix which is having 1, 2, 3, 4, 5, 6, 7 rows. And here we are seeing a matrix which 1, 2, 3, 4, 5 columns. So what is the size of the matrix? It is 7 by 5. So we are having a 7 by 5 matrix. Among some elements are non-zeros and some elements are zeros. Now let us see the next slide. Here our 7 by 5 ordered matrix has been decomposed into product of 3 matrices, where this is called U, and this is called D, and this is called V transpose. Okay, where V is it's a column matrix. It's trans. Okay. So what we have observed, our A, which is of size 7 by 5, has been reduced to U D V transpose, where U is having how many rows? Count 1, 2, 3, 4, 5, 6, 7, and how many columns? 2 columns. So 7 by 2. And D is a diagonal matrix of size 2 by 2. And V is a matrix of 2 rows and how many columns? 1, 2, 3, 4, 5. So 2 by 5. So here 2. So 2 denotes the rank, generally the rank of the matrix. That is why we can decompose it like. Okay. So 7 by 5 can be decomposed into 7 by rank, rank by rank, rank by m by rank, rank by rank, rank by m. Like that we have decomposed. So this is our resultant matrices. This is U, this is D, this is V transpose. Here you can observe that when you make dot product of these two columns, say this is x1, this is x2, you can observe that x1 dot x2 is 0. You can check. This into 0, 0, this into 0, 0, 0, 0, automatically 0. So these two vectors are orthogonal. And you can check that the norm of this x1, norm of x1 is 1. That means if you calculate root of 0.18 square plus 0.36 square plus 0.18 square, 0.9 square, it will be approximately equal to 1. Approximately, need not be exact. It will be like 0.99 something. Similarly, the norm of x2 will also be 1. So what we say, U is an orthonormal matrix. Similarly, you can check for this V, for this V transpose, if you see it as V, this vector will be unit vector, that is norm of this vector is also 1 and norm of this vector is also 1, and these two vectors are orthogonal to each other. So V is also orthonormal, U is orthonormal, V is orthonormal, and D is a diagonal matrix. You can see except diagonal means remaining all zeros. And you can verify that this is non-zero and this is non-zero. Both are non-zero vectors. Okay. So in this way, we have decomposed. Here we have seen singular value decomposition of the given matrix, given data matrix, right? Where A is of size 7 by 5 and we have decomposed it into U, D, V transpose. Okay. Now we are circling among these two are the eigenvalue, the singular values. You can say singular values. Okay. Among these two singular values, we are picking the singular value which is bigger among these two. Among these two, 9.64 is bigger than 5.29. So we have selected 9.64. And we are ignoring the smallest one. So automatically we cancel the column related to this cancelled singular value. What are the columns related to this cancelled singular value? That is the second column of this matrix and the second row of this matrix. So what happens when we cancel the smallest singular value and corresponding orthonormal vector from U and the corresponding orthonormal vector from V, automatically then we'll get a new matrix with this, like this is the new matrix U bar, this is the number D bar, and this is V bar transpose. And when we multiply, you'll get a new matrix, and that gives you the reduced matrix, which is like this. Okay, by multiplying the resultant matrices. Okay, this is the eliminated. We have eliminated the second column. We have eliminated the these three elements, and we have eliminated the second row, and we are multiplying these 3, and we'll get this. So what we have removed these unnecessary data columns, and hence our data has been reduced to this much. This is called dimensional reduction. Initially it is 7 by 5. Now you can easily understand this is 1, 2, 3, 4, and 1, 2, 3. Approximately is a 4 by 3 matrix. So you have reduced the dimensions from 7 by 5 to 4 by 3. So in this way, singular value decomposition plays an important role in reducing the dimensionality of a given data matrix. Okay, and further you can reduce to a reasonable extent. Okay, so that the content will preserve, but the storage space will be reduced. That is the motive behind reducing the dimensions. Okay, and this is how the singular value decomposition plays an important role. And the singular value decomposition is one of several techniques that can be used to reduce the dimensionality, the number of columns of a data set. Why would we want to reduce the number of dimensions? Simply, it reduces the space, storage space, and it preserves the essence, and it saves our time. So these are the advantages. And okay, well, computations will also be easy when we reduce the. And while SVD can be used for dimensionality reduction, it is often used in digital signal processing also. Not only dimensionality reduction, the second most important application of SVD is digital signal processing for noise reduction and image compression. Okay, in medical diagnosis and other areas. Okay, these are very important applications of singular value decomposition in various fields. Okay, so we can have an algorithm based on SVD. We'll have an algorithm which is called the SVD algorithm, which we use in MATLAB or by other softwares to reduce the dimensions. Okay, which plays an important role in machine learning. Okay, and sparse data refers to rows of data where many of the values are zeros. We generally in our machine learning will come to a data matrix with most of the entries are zeros, zeros, and ones. Zeros, ones are like that. Zeros. Okay, those kinds of matrices are called sparse data matrices. So sparse data matrices are the matrices which contains most of the entries are zeros. So this is often in the case of some problem domains like recommender systems where user has a rating for very few movies or songs in the database and zero ratings. That means here zeros represents the low attention towards the movies. If the data represents about some movies in a OTT platform like Netflix, the entries 1 means which is having 1 rating, 3 means which is having rating 3, 5 means which is have 5-star rating, 0 means the not at all interested movies. So, or not at all interested songs. So you can remove those songs or movies. Okay, so that, and you can replace with the new movies, and you can improve the efficiency of your OTT platform or your music platform. Okay, craze in the customers. So you can see applications of sparse data improvisations by using SVD, recommendation systems, customer product purchase. See, when you go to Amazon or Flipkart, they'll automatically bring forth the things which are you are most interested. That means, suppose being students, you are generally interested in electronic gadgets like electronic watches, mobiles, something like that, or music systems. You're generally are t-shirts like that. So whenever you log into Amazon or Flipkart, it will automatically recommend the products in which you are mostly interested. Okay, now this is possible due to the collaboration of learning and machine learning and artificial intelligence, and the mathematics behind that is SVD. And user song listen counts. So when generally we are interested to listen to some genre of songs, some people are more interested to listen melodious songs. Some people may be interested to listen devotional songs. Like that, we have some specifications, our own reservations. So accordingly, the music providers will make some recommendations to you. This is a part of artificial intelligence, and SVD plays important role. And movie ratings. Okay, text classifications. When you are searching for something, it will search. It will bring. It will regroup the text which are you are most interested. Okay, and these kind of some examples you can see. Okay, where SVD plays a very important role in the background. Now, image, let us conclude. I'm going to conclude the lecture with a beautiful example application of SVD in image compression. Digital image, today digital image processing is playing a very important role. Okay, so we are going to see an example. Image compression. First, let us understand what is matrix representation in digital image processing. Digital image is represented by a matrix and the entries are called pixels. Okay, now we are having a pixel matrix. Every image is represented with pixels, like 400 by 200 pixels. Even when you are applying for some exams, they will put some constraint like your image size should be confined to these pixels, like 1200 to 600 size of passport photos should be. I mean, you have to post like that. They are so you know what is pixels. Okay, so the digital image will be represented with the matrix of that where each entry is represented in pixels. Okay, pixels. Generally, for example, black and white image is represented with 256 and 0. That means when you have a black and white photo, it will be represented with 0 by 256 or 256 by 0 matrix. Okay, and all other colors ranges between 0 to 256. Red color with some 240 and blue color with 220, like that. There will be some specification for all the colors between 0 to 250. So when we have a digital image matrix which is divided into pixels like 1200 into 600, you can decompose it into singular value decomposition, UDV transpose. Okay, and among these diagonal values only R values will be aligned, that is non-zero. Remaining values will be zeros where R is the rank of the matrix. That is what you understood from these two sentences. And if R is small enough, the above process will significantly save the memory storage space. As low as the R, as low as the storage space. Okay, so the storage space depends on the size rank of the matrix, that is R. Okay, if R is not small, then we have to use a lot of memory to save the data. Okay, so for memory reduction, generally this is the constant Mn. Whenever Mn greater than or equal to R times of R plus M plus N, you can go for further decomposition of matter, further singular value decomposition. You can re-decompose, you can re-decompose. You can go for the iterations until and unless Mn, this condition fails. Okay, this condition fails. That means whenever Mn less than R plus M plus N, then you can stop the decomposition. But whenever Mn greater than or equal to R times R plus M plus N, you have to go for further decomposition. So here we are seeing the image of great scientist Albert Einstein. Okay, its rank is 202 and it has gone for 31840 iterations. That means it has been originally its pixels, the size is in lot of thousands, and you have done 31,840 iterations, singular value decomposition, 31,840 singular value decomposition for the pixel matrix. And at this stage you got maximum, you reach maximum extent. That means if you go further reducing, you lose the meaning of the photo. That means photo will be disturbed. So this is the possible extent where we can do iterations, 31,840 iterations. Okay, and you have reduced 58%. You have reduced 42% of the data. You have removed 42% of the dimensions from the original photo, and you have saved 58%. Still, the essence of the photo is same. That means the original photo and reduced photo are almost seems same. Okay, even though we reduced 42% of the data, removed 42% of data. See here, when you go further reduction, okay, that means when you reduce uh, okay, see, when you reduce 61% of the data, the photo is very blurred. But when you reduce 23% of the data, then photo is little more clear. But when you reduced only 12% of the data, photo is more brighter. But when you confine to only reduction of 5% of the data, the photo is almost as equal as the original photo. So this CR represents the percentage of reduction of data. 5% reduction, the original photo and the reduced photo are almost same. 12% reduction, the photo is like this. 23% reduction, the photo will be little blurred. And 61% of reduction, the photo is almost blurred. Okay. So it decides. Here, you are seeing a lady, eyes of a model. And when it is compressed, see, this is the original photo. This is the original photo. This is a compressed photo. That means you may have lost some information, but the essence is preserved. You cannot feel much difference among those two. And the difference between the lost information is represented with this thing. This is the uh, amount of information that you have lost from this photo, original photo, to the compressed photo. The difference amount of information is represented in this blurred image. Okay, ఈ information loss అయినా కూడా you don't have any loss in the original photo. Almost both are same. Okay, that is what you see. Here, when you too much compress the photo, it is all blurred everywhere, and you lost this information. You lost this information for this sake. Okay, so too much of compression makes you to lose more essence. That is what this is. Okay, so these are the advantages. All these are background needs singular value decomposition. All this image compression or image improvisation involves the role of singular value decomposition in the dimensionality of reduction. So in the next class, so in our today's class, we have discussed what is eigenvalue, what is eigenvector, and how the eigenvalues and eigenvectors play an important role in singular value decomposition. And we understood what is singular value decomposition of a given matrix U, D, V transpose. And we have understood the relationship between eigenvalues and eigenvectors between singular value decomposition. And then we have seen some applications of singular value decomposition. And we have concluded with an example of image processing with singular value decomposition. In the next class, I'll present a problem on singular value decomposition. I'll take a matrix and I'll tell you how to decompose it into singular value matrices. Okay. So with this, I'd like to conclude my class, and thanks for your patience listening. Have a nice time. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.